Good day, viewers. You are welcome to Corrosive Online Tutorial, where complex problems are made easy. In today's video, we'll be discussing kinetic theory of gas. Okay, as the name suggests, kinetic, it means motion. Okay, it's kinetic. So, the kinetic theory of gas is an assumption or a postulate about the behavior of an ideal gas. Okay, an ideal gas is a perfect gas. And a perfect gas is an imaginary gas. So you can use any of the terms. Ideal, you can use an ideal gas, okay? You can use perfect, and you can use imaginary, okay? So this is the postulate of the kinetic theory of gas. It talks about the behavior of an ideal gas. It's different from the real gas or the laboratory gas. You can watch my video of the difference between an ideal gas and a real gas, okay? But today I want to focus on the kinetic theory of gas, the postulates. Now, what is the first postulate about the kinetic theory of gas? Now, number one, it said that the molecule of the gas move randomly along a straight line. Move randomly along straight lines. Okay, colliding with one another, and with the wall of the container. So this is the first postulate about the idea of perfect gas. Okay, it said that the molecule of the gas move randomly. Underline this word, randomly, along a straight lines, colliding with one another. Okay, and not only that, with the wall of the container. In fact, when they collide, this collision of the gas molecules brings about pressure. And the pressure of the gas is due to the collision between the gas and the wall of the container. Between the gas molecule and the wall of the container. That is what results to pressure. Pressure is not as a result of the collision between two gas molecules. No. What brings about the pressure is when a gas molecule collides with the wall of the container. Okay, so this is the first postulate about the kinetic theory of what? Gas. I mean an ideal gas or a perfect gas. Now, and to illustrate this, it means that if this is a gas molecule, it goes randomly like this, move in different direction, okay? Unlike this one, the molecule of the gas does not move like this. So this is a curve, it's not a straight line, okay? Like this, you go like this, or you now have it like this, or you have it like this, or you go like this. No, the molecules of the gas does not move like this. What the first postulate of the kinetic theory of gas is saying is that the molecules of the gas move randomly in a straight line. And as they move randomly, they collide with one another and with the wall of the container. Now, the number two postulate says that the collision of the gas molecules are perfectly elastic. Okay, the collision of the gas molecule are perfectly elastic. The collision of the gas molecules are perfectly elastic. So there's a word I want to explain there. Of course, collision when they collide. Okay, molecules of the gas, of course. The word perfectly elastic, what does it mean? It means that the total energy of the gas molecules before they collide is the same with the total energy of the gas molecule after the collision. For example, let's say X is a gas molecule, is coming together, is colliding with Y, a gas molecule. Let's assume that X molecule has 10 joules of energy, while Y molecules have 20 joules of energy. You know, if I add these two together, I will get 30 joules of energy. Now, what this second postulate is saying is that if they collide, X might be going with 5 joules, while Y might be going with 25 joules. At the end of the day, if you add 5 plus 25, you will still get 30 joules. It means that there is no energy lost. So when we say the collision of the gas molecules are perfectly elastic, we are saying that there is no energy loss, because whatever is lost in X is transferred to Y. So at the end of the day, there is no energy loss. So we say that the collision of the gas molecules are what? Perfectly elastic. I hope that is clear. Now, number 3 postulate of the kinetic theory is that the actual volume occupied by the gas molecule is negligible. That's number 3. The actual volume, number 3, the actual volume occupied by the gas molecules is negligible. Negligible. The actual, why? Because if you put a gas in a big container like this, it will fill the whole container. While if you put a gas in a small container, to take the volume of the whole container. So you see, if you put it here to fill the whole place, you put it in a small container to take this volume. Because of that, we can say that the actual volume occupied by the glass is negligible. Okay, that is the third assumption or postulate of an ideal gas. Now, number 4 says that the cohesive force between the gas molecule is also negligible. Number 4, the cohesive force between the gas molecule is negligible. Yeah, you can see that the molecules of the gas, the work of the cohesive force is to bring the molecules of the gas together. But in the case of gas, it's not so. Because you have one gas molecule here, on that one here, on that one here, on that one. They are moving randomly. They are far apart. So the cohesive force is not playing any role there. So we can say that the cohesive force between the gas molecules is negligible, because the work of the cohesive force is to bring the molecules of the gas together. But in this case, they are far apart. So we can say that the cohesive force of the gas molecule is what? Negligible. Okay, I hope that is understood. Then the last one talks about that the temperature, that is number 5. The temperature of the gas is a measure. The temperature of the gas molecule is a measure of the average kinetic energy, okay, of the gas particles. So the temperature of the gas molecule is a measure of the average kinetic energy of the gas particle. Now, what are we saying here? Look at the word average kinetic energy. That means if you increase the temperature, you increase the kinetic energy of the gas molecules. Because at higher temperature, the gas molecules will gain more energy. Okay? And we said average because the molecules of the gas travels at different speed. So in that case, we talk about the average, taking the average of them. Talk about the average kinetic energy. So if you increase the temperature of the gas molecules, you also increase the average kinetic energy of the gas molecules. Okay, now when we talk about gas, there are 4 major parameters that we use to explain or describe the behavior of gas. There are 4 major parameters. Those parameters, number 1 is volume. Number 2 is temperature, in no particular order. Number 3, mole. Say mole, which is the amount of substance. Number 4, we have pressure. we have pressure. So we use these four parameters to describe the behavior of an ideal gas. An ideal gas obeys all the gas law, unlike real gas. Real gas does not obey gas law except under certain conditions. Okay, but let's focus on that on this one today. Now, when we talk about the volume is measured in either centimeter cube, cm cube, dm cube, liters, or meter cube. Okay, we can express the volume in any of these units. While the temperature, we can express it in Kelvin or in degree Celsius. Degree Celsius. Okay, and you know the connection between the Kelvin scale and the degree Celsius. Okay, Kelvin is equals to 273 plus degree Celsius. If you want to come, and when we calculate anything in chemistry, we always use the Kelvin scale. Okay, the Kelvin temperature to do our calculation. So if you are given in degree Celsius, you can convert using this formula to degree what? Or to Kelvin, because we don't put degree in Kelvin, just Kelvin. But if it is Celsius, we say degree Celsius. Okay. Then mole talks about the amount of substance. Okay. The mole talks about the amount of substance. It could be the mass of the substance over the molar mass or the relative atomic mass in the case of an element. Or we can say it is the volume of the substance over the volume at STP, which is 22.4 dm cube, or you say that is 22400 in centimeter cube. Okay. Or you say the mole is also the number of atoms over Avogadro's constant. Okay, you can express mole with these three formulas: number of atoms over Avogadro's constant, or you can say the volume of the substance over the volume at STP, which is 22.4 dm cube or 222,400 cm cube. Or you can say mole is the mass of the substance over the molar mass if it's a compound, or the relative atomic mass if it is an element. Then the last one is pressure. We express pressure. The unit of mole is gram per mole, of course you know. Okay, and the unit of mole is mole. That's it. It's mole. It's mole because the unit of mass is gram. The unit of molar mass is gram per mole. Okay. Now the unit of pressure. Pressure can be expressed in any of these one. You can say millimeter mercury. You can express pressure as millimeter mercury, or you can express pressure as Pascal. You can express pressure as Newton meter square, Newton per meter square. You can express pressure also as atmosphere. Also, in that case, you can express pressure also as Torricelli. So we use the word torr. These are all units of pressure. Okay. So in my next video, I'll be discussing the gas law in much details. Thank you.